Well, I want to first thank Ixi for inviting me today. Thank you, Freddie, for a great introduction. Thank you, Pierre, and thanks to all of you for coming today. And as Freddie mentioned, today I'm going to talk about how to best a pretty general problem that some of you may already be working on, which is how to best combine machine learning and physical knowledge to get the best of both worlds. And because it's my specialty, I'll be focusing on the data-driven model of a subgrid scale atmospheric convection for climate modeling. But hopefully the methodology that I will present today should be cross-applicable across different fields of physics. So as a reminder, I am sharing my screen, right?
You are on.
Yeah.
Did you close your mic? Because people outside are complaining about an echo. Did you close your mic?
Sorry, I put myself on. Okay. Sorry, I put myself like this? Yes. Is there still an echo now?
Please continue.
Okay, great. Okay. Great. I'll restart the movie. So this is a beautiful movie of atmospheric convection, which can be broadly defined as any atmospheric motion driven by air density differences. In the climate system, often it comes from the sun heating the surface, which, for example, is happening here, producing a storm during the North American monsoon. And what you can immediately see is that atmospheric convection is very effective at transporting tracers vertically in the atmosphere. Here you can see that it's really good at transporting dust, but it's also transporting, which is really important for the climate system, water, different phases of atmospheric water, as well as temperature. And because atmospheric convection is responsible for a lot of the fast vertical energy transfer between the surface, the atmosphere, and space, it's really important to be able to resolve convection in our climate models if we want to make reliable long-term projections. And so we would love clouds and convection in our climate models to be represented like what I'm showing you here, which is a picture taken from the window of a plane. But in practice, because for climate projection, we have to run large ensembles of climate simulations for hundreds of years, we forced to make computational compromises, and then we have to run them on very coarse grids, and clouds in climate models look a lot more like this. And this coarsening, and I should probably eliminate that vertical bar, which I believe can be done here. I don't know.
You can only move it, I think. I don't think you can remove it, but you can move it somewhere else on the screen where it's less, you know?
Maybe. Maybe I'll put it here. Okay, well, I think it's better to hide some of the citations than the title. But I will send the slides. So if you're interested in all the bibliographical references, you will have access to them. And so because of this distortion of clouds and convection in our climate models, that's why for a given emission scenario, cloud processes are still responsible, the largest source of uncertainty in our climate projections. And that's the first motivation of this talk. We want to try to decrease this uncertainty. Now, the second motivation is that this is really good news. For a little more than 15 years now, different centers around the world have been able to gather enough computational powers to run what we call global cloud resolving models. So those are atmospheric models that are run with a grid spacing that is fine enough to resolve deep convection, so large storm systems. This is typically less than 5 kilometers in horizontal resolution. And this is great because this solves a lot of this uncertainty that we mentioned earlier, because storms and the effect on climates are much better resolved. The problem is this is so expensive that you cannot run this for hundreds of years, at least not 2060. However, what it does give you is a ton of data, and that's a ton of data you can learn from with machine learning algorithm, which is the theme of today's session. And what you can do is you can train machine learning to accurately mimic the effect of the fine scale convective processes on the large scale climate. And to make this more concrete, I'm going to show the setting I'm going to use for most of this talk, which is based on what we call the super parameterized model, which is a combination of two things. And let me see if this works. Okay, great. On the left, it's a coarse model with a resolution typically of 100 kilometers, so that you can think of that as more like the traditional climate models we currently use. But the difference with the traditional model is that, and it's a compromise between the traditional climate model and the storm resolving models I showed you just earlier, is that within each grid cell, you embed a two-dimensional storm resolving model that then can resolve the effect of the fine scale convective and storm processes, as well as fine scale turbulence on the large scale climate. And the advantage is that this setting makes it pretty straightforward to machine learn this process, because all you do is you learn the effect of this two-dimensional storm resolving model, and then you replace it with a neural network. And once plugged back in the climate model, it can make the model up to 10 to 20 times faster with minimal accuracy trade-off compared to resolving storms, which is way more computationally expensive. And so, therefore, I'm going to show you different versions of this parameterization, but all of them go from one column that represents the large-scale climate state to how convection and subgrid scale processes redistribute different thermodynamic quantities in the vertical. So it takes insolation, the full vertical profile of temperature, the full vertical profile of water vapor mass concentration, as well as surface energy fluxes. And its role is to output how these fine scale, the subgrid scale processes redistribute heat in the vertical, water in the vertical, and then radiative fluxes, because we need them when we make climate predictions. Now, without further ado, this has now been done for a few years by several labs around the world. Here I'm showing one from the lab I was in. The work was led by a student, Griffin Moores, and he did it in an Earth-like setting. And you can see the truth. So that's the super parameterized model we're trying to learn on the top. Moistening, so that's how water is redistributed with height at one level. We're trying to predict the whole thing, but here I'm showing you one level on the left, and then how you redistribute heat, temperature on the right. And what you can see is upon visual inspection, this looks pretty good. It's incredibly accurate, especially given the complexity of the task at hand. And this asks a really provocative question, and that question is, especially if you combine it with recent results in data-driven numerical weather prediction. So here you're seeing a forecast that was made 1 month in advance by a convolutional neural network, and there was no dynamical core. So it was just a neural network that was set up in an iterative way, and it's able to predict the near surface temperature, which is a societally relevant variable, up to 1 month in advance with great accuracy. And so this is kind of a shock in the community. And you know, can we avoid explicitly encoding physical knowledge in the algorithms we use to make atmospheric prediction, even if you're still going to need physical models to train those models? And the point I'm going to make today is that while it could be a possibility for initial value problems like meteorology, for long-term climate projections, we more with in a boundary value problem where you're trying to resolve the effect of a small perturbation on the entire Earth system. And you want to predict the long-term evolution when the Earth is exposed to condition it may have never been experienced. And the reason I think we can't completely eliminate physical knowledge for long-term climate prediction is for 3 reasons that I'm going to get into right after this slide. Physical consistency, interpretability, and failure to generalize when conditions change. So for the first one, physical consistency, the problem is that if you just train a neural network to emulate subgrid scale processes like I showed you earlier, without any constraint, it's going to take shortcuts and it's going to violate conservation laws. So I'm going to show you a histogram of the residual from the mass conservation equation at the top and the moist enthalpy conservation at the bottom. You can think of the moist enthalpy as a convenient measure of energy for atmospheric convection. And if the neural network was perfectly conservative, we would get something that looks like a beautiful delta function near zero. Now in practice, when we feed the batch through the neural network, we get a lot of residuals, and we get residuals that far exceed the top of the atmosphere change in response to a doubling of CO2. And that's what we're trying to resolve when we're making climate change prediction. So this is really problematic. Now, the second problem I want to tackle is the problem of interpretability and trustworthiness. Here I'm showing a movie of a bad neural network that was coupled back to the climate model. It's not awful, but it's definitely not the best fit. And when you fit it back and you couple it back to the climate model, it leads to really dramatic instability. And in that case, we were lucky enough to be able to resolve the instability. So you can see on the right, the model crashing after one day. You can see beautiful internal gravity waves being emitted right before the model crashed. And if you don't know a priori if the model, if the neural network is going to crash the model or not, why should you trust it? And that's why we need to develop interpretability, trustworthiness, and understand which machine learning models are reliable and which are not. Now, the third problem is failure to generalize. So here I'm showing you a typical prediction problem I'm going to tackle today. So here the problem is to predict how convection redistribute water vapor in the vertical in the tropics. And I'm training a bunch of different neural networks for that task in a reference climate. And they all do pretty well. And this include neural networks that I've engineered so that they conserve mass and energy. But now if I warm the climate by 4 Kelvin and I ask them to make the same prediction, they all fail by a big factor. Like you can see, especially in the bottom of the atmosphere here, they fail by a factor of 5 to 10. So this is a really dramatic inability to generalize and also motivates using physical knowledge, which can help us make more general predictions. And so the 3 problems motivate what the question I want to tackle today is how can we design data-driven models of convection that are still interpretable and physically consistent, which is related to that more general question of how do you best combine, machine learning for accuracy and physical knowledge, in that case, for interpretability, reliability.
A graph problem. So let me tell you
and this question motivates now a whole field because things are evolving so fast. I would say now it's an entire subfield called physics-guided machine learning, which aims to restrict the output of machine learning or a statistical model so that they only yield physically plausible solutions. And I'm going to argue that we have a long history of doing that in the atmosphere, and you can we can simplify it by ranking it in terms of physical structure. And I think where we have a lot of history is trying to learn the parameters of a physical model. So you have a fixed physical models and you leave a few free parameters and we're trying to best estimate it. And that's an entire field called data assimilation, which try to, it's usually in a Bayesian framework, try to find the best estimate for these parameters. And in that case, you're an example where you have a lot of physical structure because you're doing it within a physical model. So you'll never be able to represent what the physical model does not capture, even if you find the optimal parameters. So it's nice, it's reliable, but it may limit your expressiveness a little bit. Now, a slightly more flexible version is what you get when you look at the meteorological forecast on your phone, is that it's called model output statistics. So we run numerical weather prediction models globally, but then they never give you the right prediction, in your exact village behind the mountain where it rains more than in the village next to it. And so then we use observations to train or I should say meteorological centers, train models, usually pretty simple models like multiple linear regressions, to bias correct the physical model so that then they capture that one village rains and the one next to it doesn't. And so that gives you a bit more flexibility because the statistical model is freeform. But what I'm going to show today is the limit where I get as much representation power as possible. So I'm starting from a neural network and I'm just adding the minimal amount of physical knowledge to gain back interpretability, reliability, ability to generalize. And now I only have 30 minutes apparently, so I'm going to zoom through the 3 different solutions we found. But if you have any questions, we can come back and slow down for the point you're most interested in. So let's start with physical consistency. So how do you enforce conservation laws? And I'm going to show you 2 different methods of doing this. So the first method that you most commonly find in the literature is to enforce physical constraints by modifying the loss function. And the reason it's the most common method is that it's very easy to do and it's pretty reliable. And so the idea is simply you take your normal loss function, and so imagine you take mean squared error for performance, and then you add a term that just punishes the neural network whenever it violates conservation law. So you can think of it as a Lagrange multiplier. You can formulate it using any norm you like. So you just, for example, use the norm of the residual of the physical conservation equations you're interested in, or the state equations you're interested in. So that works pretty well. The problem is that you're still subject to optimization, and in that case, it's stochastic optimization, so you're never guaranteed to reach 0. So in the climate settings, this is problematic because you'll never reach 0 residual, so you'll always be creating spurious mass, spurious energy at every time step. And so we try to come up with a pretty general way of enforcing physical constraints to within machine precisions. And we developed that using what we call constraint layers. And we try to make it as simple and general as possible so that it could work for any nonlinear analytic constraint. So as long as you can write it down, you can enforce it. And I'm going to briefly go through the idea for a neural network. So imagine you have a problem with m inputs and p outputs and n constraints. The trick is instead of outputting p outputs, you output p minus n direct outputs, and then you use fixed constraint layers to calculate residual output so that the whole constraints are exactly enforced. And so far it's pretty simple. And the only trick is to write that in your favorite machine learning library like TensorFlow, PyTorch, and you do it within the neural network. And so then when you optimize on the full input. And so when you backpropagate and you adjust the parameters of the optimizable standard neural network, the final weights and biases of the neural network will depend on your constraints. But you still expose the full output to the loss function. And so this is a way of enforcing the constraints to within machine precision without trading accuracy. And this is published in PRL at the bottom. And feel free to read it for more details and why it's often nicer than the loss function, even if it's a bit more work to change the architecture of the neural network. And so the summary is that it is possible to enforce conservation laws in neural network. In our case, you conserve mass, energy, and radiation. And we can switch to the second problem, which is trustworthiness and interpretability. And that's a problem that's particularly important in climate science because we're trying to make societally relevant prediction, possibly inform policymaking. And so it's really important for us to be able to interpret the models we produce. And so our idea to gain more intuition on whether we could trust or not the machine learning models was to adapt explainable artificial intelligence method from the simplest to the slightly more complex one to the particular physical case we were interested in. And so I'm going to show you 2 different methods that can be adapted and tailored to the particular case of atmospheric convection. The first one is called partial dependence plot. It's as simple as it gets. You just take the prediction of your neural network and you average it over inputs of interest. So it's a conditional average to see how the prediction of your neural network depends on a group of inputs you're interested in. And in our case, we're going to do it by changing mid-tropospheric moisture, so that's the amount of water vapor that's in the middle of the atmosphere, and that's what we know fuels storm. And so we start from a really low amount, and we try to increase it step by step to see if atmospheric convection reacts the way we expect from observation and the research literature. And so you can see here, as we increase mid-tropospheric moisture, the storm, so a meteorologist would recognize that as a storm becoming more and more intense. As a physicist, you can see it by thinking of energy transfer between different components of the energy. So as the storm intensifies, you can see that more and more water vapor is transported upwards, and then it's going to condensate into liquid water and ice and then precipitate. And so you have this typical signature of drying, and as the water vapor changes phase to become liquid water, energy is released in the form of heat. So you have this combination of drying and heating. And so that allowed us to gain.
I didn't get why you call this partial dependence plot.
Just because we calculating the prediction, so in that case, it's a full profile, and we conditionally averaging it on the value on tropospheric moisture, so it's a partial dependence with respect to QM.
Okay.
And then we fix all the other parameters. So for example, here we fix what's called lower tropospheric stability, which is a potential temperature difference, which also controls if convection will fire up or not. And we played that game for a bunch of different inputs that we knew were important as atmospheric scientists.
But how is this related to your machine learning?
This is a prediction of the machine learning algorithm, and it behaves like we expect. And so we're happy because it doesn't give you absurd results when we change. When we crank up tropospheric moisture, it behaves like real storms and not something fake. So it's a really, that's like a simple first check. It's like, does it look physical at all? And I'm going to go into a more advanced second check to answer that question of stability I showed you earlier. And what we're doing is we're taking advantage of the fact that when you train a neural network to optimize using what's called automatic differentiation, which is a very computationally efficient technique to calculate the gradients of the loss function. But now what's nice as a physicist is that it means it calculates the Jacobian of the system super quickly. And so Jacobians that could be normally very expensive to calculate because you have to do a ton of little perturbations and forward experiments. Here you can get it for a fraction of a second, in a fraction of a second. And once you have the Jacobian, depending on your application of interest, usually you can use it to make a simple, for example, stability or wave predictions. And so in our case, if we couple it to two-dimensional linearized gravity waves dynamic, you can get the full stability diagram corresponding to the internal gravity waves and whether they're going to amplify or not. And so here the growth rate is in the vertical, the phase speed is in the horizontal, and the entire blue space here corresponds to unstable growth. And so although we expect the middle to have some growth because that corresponds to slow amplifying modes that we know exist in the tropics, all of this we know is spurious. And if you look at the phase speed and the growth, it actually matches what we saw in the simulation right before it crashes. So those are just, and sorry, I should. Then we use that, once you have that, that means that before even coupling the neural network back to the climate model, you know if it's going to blow up or not. And so now we can already, before even coupling it back, sort the neural networks into those that we know are reliable and those that we know aren't reliable. And this also allowed us to, for example, find tricks to eliminate the instability. And so those are just two examples of how you can tailor methods that already existed in the computational literature to your case of interest. And today, I only showed partial dependence plot and gradients. But right now, if you look at the climate science literature, especially, attribution maps are really taking off. When you train a convolutional neural network, you can look at the inputs that activate the outputs the most. And right now, people are finding a ton of patterns and sources of predictability that we're not able to find before using machine learning. So that's another example of how to creatively use those explainable artificial intelligence technique, in that case for scientific discovery. And I think we're only scratching the surface, especially because a lot of those methods are coming back. So I really encourage everyone for your field of interest to think of how to creatively use this method, because you can gain not only trust, but you can also potentially make scientific discovery for your system of interest. And now I don't have much time for the last one, which is my most recent work, which I think is quite exciting. It's the challenge of generalization. It's quite exciting because it's a really hard challenge. And so since I'm a physicist, my first reflex was to first like break the model even more so that I knew how to solve the problem. And so the very, very drastic generalization experiment I'm going to be looking at is I'm going to train in the cold aquaplanet. So that's an ocean world simulation. And then I'm going to warm it not by 4 Kelvin, but by 8 Kelvin. And then I'm going to train and validate the model in the cold aquaplanet and then test it in the tropics of the warm aquaplanet it has never seen. And so, sorry, I'm going to skip that. And so if you remember the previous failure mode that I showed you, now it's extremely dramatic. Now I don't fail by a factor 5 to 10, I fail by a factor 100. And the reason I like that is that when you fail by a factor 100, you're not you're not adjusting the epsilons anymore. You can really see which solutions work and which do not work. And our idea, which was based on the self-similarity in fluid mechanics or domain adaptation methods in machine learning, was to physically rescale the data. That's why we use knowledge of the climate system to transform what's a difficult extrapolation problem for the machine learning algorithm into an interpolation problem that is much more likely to solve. So if you look at the mapping here, going from the climate state to the subgrid scale thermodynamic tendencies, what I've shown you initially, and that's why I really wish the bar wasn't here. So maybe the bar will move temporarily. Okay. Okay, so maybe I'll just say it.
Take it the green.
Oh yeah. Maybe. Oh, but now it messed with this one. Sorry. I'm not sure what happened. Maybe I shouldn't have done that. Okay. I think I'm back. Okay, so what we saw initially is that because we have this dramatic failure mode, what it suggests is that if we just learn this mapping in the cold climate, it's not the same mapping in the warm climate. But now we want to try to rescale this mapping so that the mapping we learn in the cold climate in the same is as similar as possible in the cold and the warm climate. And for the interest of time, I'm just going to show you one way, the input rescaling in our case that mattered the most. And that was the one linked to the mass concentration of water vapor in the input vector, which is a specific humidity. Because of the Clausius-Clapeyron equation, the amount of water vapor a given air mass can hold before it condensates into liquid water increases quasi-exponentially with temperature. And so what that means is that hot air can hold a lot more water vapor than cold air. And that's why if you look at the histogram of this concentration, it's very different between the cold and the warm climate. But the nice thing is we know the Clausius-Clapeyron equation, so we know the maximum amount of water vapor a given air mass can hold. And so we can use this to rescale the specific humidity and derive relative humidity. And in our case, we can do that either as a custom layer or a data generator, but you can do it within the neural network. So you can test a bunch of different physical rescaling. And now you transform what's an extrapolation into a quasi-interpolation problem. Of course, here I'm only showing you the univariate probability density function. In general, you want to make the joint probability distribution density function align as much as possible. But you can play this game with this input and then other inputs. So sorry, this already dramatically improved the generalization for one profile, but also if you look at the whole mean squared error, so it's statistically significant. And then you can keep playing that game for every variable. And I'm going to jump to the conclusion so that we have time for questions. We scale temperature to buoyancy. We scale latent heat flux using the surface aerodynamic flux formula. We made it work in aquaplanet, but we also made it work in the real geography where you can see in the tropics that the error is mostly going down. And I'm going to jump to the conclusion. This is a little pitch that all I've shown is incorporating physical knowledge into machine learning, but a really interesting endeavor is to also go the other way around, is to try to use machine learning to extract physical knowledge from data. And for instance, in the case I just showed you, where you used physical knowledge to make a neural network able to generalize across climate, you can then use explainable artificial intelligence method to understand why it became more general. And that's where you can learn new knowledge. And we found that we had much more local mapping in the vertical, and that's why we think it's more reliable. But I'm going to skip over all of this and just jump to the conclusion slide, which I way overestimated the time as usual. Which is the main message to take away is that atmospheric physical knowledge that we have accumulated over now a century and a half can help create more robust statistical algorithm and machine learning algorithms. And in today, what I showed you is that it's possible to use physical knowledge to enforce analytic physical constraints within neural networks, approximately within, using the loss function, exactly using the architecture. We can tailor machine learning interpretability methods, and we can combine it with simple physical dynamical systems, or little physical equations we already use for interpretability to then form more creative ways of better interpret and gain trust into a statistical algorithms. And then something I'm really excited about that I showed you at the end, just by rescaling the inputs and the outputs of a neural network, you can really help them generalize, in my case, across climates, but across different regimes where it may not transfer easily. And this is exciting because those rescale machine learning algorithms learn more general mapping. And because they learn more general mapping, they are less data greedy, and they open the door to, in the atmosphere, complementing already existing data assimilation technique to facilitate using different data sources, and also to form models that can generalize to different regimes. With that, thank you, and I'm happy to take any questions. And this is